Okay, so welcome back to the third part here. And in this part, we're going to discuss what each of these problems really is. And then we might go on and discuss the implications of each of these. So, and the way to solve it, of course. So the first problem here, if I go back to the Rabiner paper, so this is the Rabiner paper, and here you can actually see that the first problem here is given the observation sequence O and a model with its parameters, how do we efficiently compute P of O given the model, the probability of the observation sequence given the model, right? So we want to compute this, and this is basically, you can kind of think of it like from the model, from any given model, what is the probability of looking at observing this data? And this is kind of what we're trying to do is we're trying to evaluate the model itself. What is the probability that this data was generated from this model and not from another model, right? So this is kind of a model evaluation problem. If you want to compare multiple models, you will have to use this. You'll have to refer to this problem. So if I give you two different models or three different models, and I ask you that this is the data observed, can you tell me which model was used to generate this data? By default, what you'll have to do is you'll have to find the probability of O given the model for the first one, given the model, the second model, or given the third model. And then for each of these, you'll then work with the for each of these possible values, you'll then start to represent these your results as a probability values, right? So you'll have three different probability values. The one which is the highest, that is going to be the most probable model from which the data is generated. So that is the first problem. The second problem is kind of finding the hidden sequence. So in this case, the model is fixed. We're not worried about the model itself. The observation sequence is also fixed. However, the states is unknown. So what is the probability that the observable sequence was generated from these states given the model and the observable sequence? So those are two things are known. The model is known. It's fixed. We don't want to change that. The observation sequence is known. However, the underlying Q is not known, and that is what we need to look into. Okay, so and of course problem 3 we've already discussed that. So those two, let us just focus on these two problems, and let us see some examples of these, and let's see what are the different algorithms. And of course, the algorithm that are given here, this is if I talk of the Rabiner paper, unfortunately this is too mathematical, and I believe this is too much of a from an explanation point of view, you won't be able to understand much from the Rabiner paper. So for that reason, we're going to skip to the summary paper, the chapter 8 paper, and in this case, here's an example, a typical example, and this is kind of very well explained in a very subtle and simpler manner. And we'll take these examples and we'll see what needs to be done and how calculations are going to be made, and some basic things. In particular, I'll explain to you this particular figure. And I think this is, if you can understand this figure, you'll be able to kind of compute the whole thing. And this is the computation of a single element and how that is done. And we'll see the different algorithms. The forward algorithm is given here. Initialization, recursion, termination, the conditions, and we will discuss this one. So in this lecture, I'm just going to focus on this one problem, the A3, the likelihood computation problem, and I'll just focus on this one. So in this case, what we are given is, we're given the model HMM with its emission probabilities and transition probabilities, and we also given the observation sequence O, and we want to determine the likelihood of observing this data from the given model. And for example, here it's taking up a sequence. Let's suppose that we want to compute the probability of 313. In this case, of course, it's just a hidden, it is just observable sequences. 313 are the observable sequences, and we can just multiply the probability of observing each with the next state, and along the arc we can just move along, and we can compute its probability really easily from a Markov chain. But think about if we take the ice cream example again, that is given in figure A2, and we observe the sequence 313. What is the probability of observing the sequence 313 from this model? So what is the probability of observing 313 from this model? The answer to that is going to be, and we discussed this in the last lecture as well, we can observe 3 in actually, if we look at it, we can observe 3 in possibly 2 different states, right? It can be either in cold state or in hot state. And for each of these, we'll have to take up a product of each of these states, right? So it is going to be, if it's 313, and let's suppose that we want to know the probability of observing these sequences. The problem is, just by looking at this, you don't know if I have to use this probability or this probability, right? So I'm not aware of which probability will be used. If it was a Markov chain, it would simply have been probability of 3 into probability of 1 into probability of 3 from the states, and that would have been it. However, it's not as simple over here. And the reason is we need to have another possible value in order to identify. And that possible value is the underlying hidden state. So this 3 is generated from hot, this one is generated from hot, and this 3 is generated from cold. If we know this, then this becomes very easy. So ultimately what we have to do is we need to have the probability of O, the observable sequences, given the hidden sequences. And if this is possible, this is known, the problem becomes really easy, really simple. It's the same thing. It's probability of observing 3 from hot state multiplied by transitioning from, yeah, a probability of 3 from hot state multiplied by probability of 1 from hot state and multiplied by probability of 3 from cold state. Because in this case, the states are fixed. Since we know the states, then it becomes very easy to find the corresponding values. And that is the exact thing that is given in this formula as well. So if I give you the hidden states and if I give you the actual sequences, the answer is very simple. All you have to do is just multiply the probabilities. Probability of 3 in hot is 0.4 multiplied by probability of 1 in hot is 1 given hot is 0.2, and multiply with probability of 3 given cold, which is again 0.1. So this is 0.4 into 0.2 into 0.1, and that's your answer if the states are known, of course. So in this case, we are given the states as well as the possible values. However, there's one small trick here, or one small issue. The hidden values, the hidden states here, these are not known. The only thing that is observable, the only thing that we get to know is that you ate 3 ice creams on the first day, 1 ice cream on the second day, and 3 ice creams on the third day. We don't know the underlying hidden sequence. And if you don't know it, what needs to be done? Well, the idea simply is that since we don't know which sequence was used to generate this, which state was used to generate it, what we'll do is we'll assume that this 3 can be generated from hot, or this 3 can be generated from cold. And since this 3 can be generated from hot or cold, 1 can be generated from hot or cold, 3 can be generated from hot or cold, right? So we need to take care of all the transition probabilities, all the emission probabilities, and perform some of them as well. And perform product of all of them. So now what this transforms up into is the probability of generating 3, 1, 3 from hot, hot, cold. So this is kind of like what we're going to do is we'll need to compute the probability of event 313 instead by summing over all possible weather sequences weighted by their probability, right? So first of all, it computes a joint probability in a particular weather sequence. So for example, big P of O and Q at the same time, and that is given by probability of O given Q multiplied by probability of Q by Bayes law, and this then translates to, you know, the observation probabilities multiplied by transition probabilities. So observation probabilities here are P of O this is observable event, right, from a hidden state Q, and then you need to transition from state to state. So for example, if you assume that it's hot, cold that generated 313, then what you need to do is you need to have probability of 3 from hot multiplied by starting in hot, right? Then probability of 1 in hot multiplied by probability of hot given hot multiplied by probability of 3 in cold multiplied by probability of cold transitioning to cold from hot, right? So those are the different probabilities. So again, you can see starting in hot, multiplied probability of hot, and multiplied probability of cold given hot. So those are the transition probabilities. Then you have got the emission probabilities: 3 in hot, 1 in hot, and 3 in cold, and it's a product of all of these. So this is the joint probability distribution of 313 and in states hot, cold. However, the problem still remains the same. Since it's not just hot, cold, we can have cold. The first three can be generated from hot or from cold. So whenever you have got this or functionality, you need to add them up, and that is where your summation is going to come up. So for each of these possible states, we'll have to come up with all the probabilities and sum them all up, which is practically impossible, because as is shown in the example here, if you want to compute the probability of 313, to compute this probability, what you need to do is you need to compute the probability of 313 from cold, cold, then add to it the probability of 313 from hot, cold, hot, add to probability of 313 from hot, cold, and all possible permutations of both of these events, which comes out to be around, if you know, each of these can have 2 possible values, and since there are 3 such values, so you'll have a total of 8 different possibilities, starting from cold, and ending up with hot, right? The reason for telling you this is that this is the actual method to resolve or determine the probability of 313 from this hidden Markov model. So if you are given observation sequence 313, what is the probability that this Markov model generated this thing? To compute that, you'll have to compute something like this, right? So probability of 313 from cold, add to it, and to compute this, I've already told you this is probability of 3 given cold, probability of 1 given cold, and probability of 3 given cold. You multiply them, and then multiply them with probability of starting in cold, and then going from cold to cold, and going from cold to cold, right? So all of these things are just to compute one probability. Similarly, compute the second probability, similarly compute third, and compute 8 different probabilities and sum them up. The problem, as you might have noticed with this kind of solution, is that it's going to take a much longer time. If you find the what do you call, the complexity of this, the more hidden states there are, the slower the algorithm becomes. The more the number of observations. So in this case, there are 3 observations. If I take 10 observations, you'll have to compute 10 different, for each of them, there's this 8 states. And then with 10, it's going to become 2 raised to power 10. And then it becomes almost impossible, or 3 raised to power 10 actually. So there it becomes impossible to kind of solve these problems. And since this becomes exponential, the complexity becomes exponential. This is too large a number to compute and to find values. So you can try this on your own. I can, I might challenge you to try this on your own and run it and see what happens. So for a very simple problem, maybe in this case there are just 3 different states and 2 possible weathers in 3 observable states, right? And even for this, this becomes almost impossible. If you've got a length of, let's say, 5 or 7, you can try that 5 or 7 different observation sequences, or observation sequence of length 5, and that is going to tell you how hard it is to compute these. And think about if it goes to this was a simple example where you had got just hot and cold weather. What about if we add 2 or 3 more weathers: hot, warm, cold, chilling, and snowy, or something like that? and similarly, you can have more states here. Instead of 3, 1 and 3, 1, 2, 1, 2, 3, you might have, 10 different states. And that tells you how does the problem explode in terms of complexity and in terms of work. So in simple words, it's not possible to solve it like that using the brute force method. So luckily, we have got a simplified method, a method that we call dynamic programming algorithms, which is going to solve the problem in a much faster way. And the main thing that you need to note is that it depends only on the previous probabilities. So all you need to do is compute the previous probability and add to it a small element. So for example, if you want to determine if I want to determine probability of 313, right? All I have to do is I have to find the probability of 3 and 1, and then multiply it with a certain other probability, the probability of 3 in cold and as well as 3 in hot, and multiply it with transitions from the previous states to the next states. If I have the probability of first two, I just need to add one small element to it, and that gives me the overall probability of the whole sequence. The way to do that, if I go along the algorithm now, is really simple. You have got a starting probability. So this is a probability of starting in hot or cold weather. So the first observable sequence is 3. The second observable sequence is 1. And the third observable sequence is 3 again, right? And what I'm going to do is I can start with hot weather or I can start with cold weather. And in each of them, I can then observe 3, right? So if I start with hot weather, for let's do it systematically, right? So the first thing that you need to do, given this problem, if you want to apply this algorithm, you need to draw this graphical representation of the algorithm. And the way to do it is you first need to write your observable sequences along this path. So this is O1, O2, and O3. In this case, it's of course 3, 1, 3. You need to have a starting point here written by lambda or pi. So this is pi. And you need to have both the observable states. So if you have 2 observable states, you need to put both of them. If you have 3 states, you need to put 3 of them over here. In this case, we have got only 2 hidden states. One is the cold weather and one is the hot weather. So you need to put both of those states here. If I had got 3 hidden states or 4 or 5 or 7 different hidden states, I'll put them all over here in this manner. After putting them in, I need to draw these lines. So what is the probability here? If I start in hot state, it is basically going to be probability of hot multiplied by probability of observing 3 in hot state. That is my first variable alpha 1. So my first variable alpha 1 is for state 2 or head state is basically probability of starting in hot state. Starting in hot is 0.8, as we can see. And then multiplying it with probability of observing 3 in hot state, which is 0.4. So 0.4 into 0.8 is 0.32. That is my alpha 1 for 2. Similarly, for cold state, again, you need to compute alpha 1 for 1, which is going to be probability of cold given start. So starting in cold state, which is 0.2, multiplied probability of observing 3 in cold state, which is 0.1. So 0.2 into 0.1 gives you 0.02 as your answer. So that's alpha 1 variable for this state and for this state. So I need, if you note, I'm starting from left to right, and I'm just computing the values. I just need to start at the first point, starting in hot and multiplying it with observing a particular value in hot, starting in cold and multiplying it with observing a value, this observable value in cold, right? And that gives me these 2 values. After these are computed, I can then compute the probability of observing 1 in hot state or observing 1 in cold state. And to do that, what I'll need to do is, there are 2 paths that are possible for reaching here, and both paths come from these 2 points, right? So what I need to do is, if I take this path, for example, this is going from hot to hot, probability of hot given hot, multiplied probability of observing 1 in hot weather. And this is first path. The second path is probability of going from this cold to hot. So probability of hot given cold multiplied probability of 1 in hot. So this part is same. However, the first part is dependent on which previous state you are visiting from. The transition probability, of course, is dependent on state, and the other probability is observing, since this is hot states, observing 1 in hot. This is kind of fixed. And what you can notice here is that this is going to be 0.6 into 0.2, and this is going to be 0.5 into 0.2. In this case, you need to take some of these values. 0.6 into 0.2 is one value, right? And you also need to multiply it, you also need to multiply it with alpha 1 value. So 0.32 multiplied by 0.6 multiplied by 0.2 plus 0.02 multiplied by 0.5 multiplied by 0.2. So those are the three values you need to multiply. These are the three values you need to multiply, and then you need to take sum of both of them. So 0.32 into 0.12 as is shown here, right? Plus 0.02 multiplied by 0.1. And if you take this sum, you then compute alpha 2 for, which is 0.0404. Similarly, we can actually try and compute alpha 2 1 again. And alpha, notice the subscript here. The subscript here indicates which state we are talking about. So this is basically the first part here. You can see alpha 1. And the hidden state that we're using, this is 1 for cold and 2 for hot, right? So you can see that. This is second variable that we're computing, and then we can have a third variable after this as well. So for second variable, this is the result for hot. Similarly for cold, there are two paths coming in, 0.32 multiplied by 0.4 multiplied by 0.5 plus 0.02 multiplied by 0.5 multiplied by 0.5, right? So this is going to be 0.32 multiplied by 0.2 plus 0.02 multiplied by 0.25. And this again comes out to be 0.69. So what I would want you to do is that I would want to compute alpha 3, 2 and alpha 3, 1 for this. And the idea is really simple again. So I can give you a hint, and this is something that you need to do, that you need to practice right away with this lecture. Alpha 3, 2 is going to be computed by, there are again two paths coming into it, right? You need to compute these two values first. These are computed now. So alpha 3, 2 is going to be 0.404 multiplied probability of hot given hot multiplied by probability of observing 3 in hot. So that's the first part. Add to it the second part. Probability of going from hot, going from cold to hot, right? So probability of H given C multiplied by the alpha 2 1, which is 0.069, multiplied by observing 3 in hot again. And if you multiply these three values, so you'll get the possible value for this edge. Now you've got value for this edge as well as this edge. Add both of them to find the alpha 3 2 value. Similarly, we can actually find alpha 3 1 by computing the values for this edge and for this edge and summing both of them together. So that is the whole thing. The alpha variables need to be computed. Alpha variable is your forward variable, and by computing these, what we are doing is we are actually taking sum of all paths to a point. All paths that lead to this edge will be summed up, and their alternate paths, and you're actually summing them up to reach this value. So for example, to this for reaching state C in O3, there are only two possible paths. You either come from the hot state or from the cold states, and that is exactly those paths, the alpha variable till that point multiplied by the weight of the edge of connecting that state to the current state. So alpha 2 1 multiplied by this edge. So this edge is transitioning from state C to C and observing 3 in state C, right? Add to it the other path, which is alpha 2 2 multiplied by probability of observing cold given that the previous weather was hot multiplied by observing 3 in cold. And then you need to sum both them up. So this is sum of all the paths coming into C, and that represents your alpha 3 1 value. And similarly, I can compute alpha 4 1, 5 1, alpha n 1, whatever it is, I can compute those. So remember, it's always that you need to start from left to right to start computing values. Until I don't know the value for this, I cannot compute the value for this. because it is going through this C. And to compute the value of alpha 21, I need to first compute the value of alpha 11. To compute the value of alpha 11, and since there's only one path through it, it is a simple product of both the probabilities, initial state distribution as well as the probability of observing this sequence, this letter inside this state, right? So what we have done so far, if you look at the way it's being visualized, all paths are coming to it, and we are just performing sum of all those paths. So there's certain alpha value for this multiplied by a1j, alpha value for this multiplied by a2j, certain value over here multiplied by alpha 3j, and these are actually this a1j, a2j, a3j, nj are nothing but basically the transition probabilities and the emission probabilities. So aij and bj, emission probability and transition probabilities, etc. And that's the whole thing. That is the exact algorithm that is being followed here. I'll not ask you questions about the algorithm. This is kind of a repetition, or you might, I'm not going to implement it. This is going to be, we're going to use built-in code for implementing it. And I'll show you the code at a later stage, maybe in the next lecture, or yeah. So, but for now, I think what you should be able to do is that if you're asked the question of computing the, given a hidden, given an observable sequence and given the model parameters, so you'll be given, for example, O is equal to 313, and you'll be given this model either in terms of text or graphically, right? And you might be asked that what is the probability that this sequence was generated from this model? That kind of question is your likelihood question. Or you might be given two different models and asked that what is the probability, or which model do you think generated this observable sequence? To answer that question, you will have to compute the likelihood of both models separately. And to compute the likelihood, what you need to do is you need to draw it like this. This is a graphical representation, the clean representation. First of all, you need to write all the observable sequences here, draw all the states here, and then draw all the paths here. And for each path, compute the relevant probabilities, compute the alpha variables, and after computing the alpha variables, only then will you be able to compute the next alpha variable. And once you're able to do that, finally you'll have at the end, ultimately at the ending point, both of these will be combining together to go to the end state. So that end state is not drawn here, but you'll have an end state which is going to be, if we go from hot to end, right, or from cold to end. After observing this, of course, you can have a probability of 1 and 1 on both sides, and that is going to sum up both of these alpha variables directly to compute the probability of observing the sequence from the model, right? So that's kind of it for now. In the next lecture, and yeah, so the final computation here, you need to remember, is basically sum of both of these values, alpha variable here and alpha variable here. You just need to sum both of them to compute the final probability of the probability that this data 313 was generated from this HMM model. So that final value, that final alpha that you get at the end of this over here is the one that reflects the probability distribution, or the probability of generating data from this model. So let's get to the next lecture, and then I'll talk about, I'll just make a small change here actually, and you'll notice that with that small change, I'll convert the problem from forward algorithm to actually Viterbi algorithm, and we'll discuss that in the next lecture. Again, let's take 5 minutes break, and let's come back and discuss it from the same point. Okay. So thank you very much, and let's see the next lecture in around 5 odd minutes.